So thank you for having me. I'm speaking to you from lovely and now dark Germany. Like David said, I'm a postdoc here at the Albert Einstein Institute in Hanover, Germany, and I mostly work on gravitational wave astronomy. I was a member of the LIGO Scientific Collaboration for 10 years, up until 2018, when our institute left. But I continue to work on gravitational wave astronomy, and in particular, looking at what sort of fundamental physics can we learn about from gravitational wave observations, and also more multi-messenger observations. That's what I'll be talking about today. There we go. Just so we're all on the same page, I'm just going to spend the first few minutes doing a brief overview of what gravitational waves are and how we do science with them. So first of all, what is a gravitational wave? Well, it's a ripple in space-time that's caused by accelerating masses. It can't just be any accelerating masses, though. You specifically need a changing quadrupole moment. And if you have, say, a binary star system, like in particular binary compact objects like binary black hole or binary neutron stars, and they're orbiting around each other, that's a changing quadrupole moment. And so that will emit gravitational waves. And I have this movie here that was a simulation done by the MPI in Golm. And here they simulated two neutron stars orbiting around each other. And these yellow here represents the gravitational wave that's being emitted. And because the stars are losing energy to gravitational radiation, eventually they end up merging. And in this case, in this simulation, it briefly forms what we call a hypermassive neutron star before eventually collapsing to a black hole. And that's the case for two neutron stars. You have similar sort of dynamics with two black holes, although you always just have a black hole in that case. And you can also have a neutron star black hole where a neutron star falls into a black hole. Gravitational waves were first predicted by Einstein in 1915 when, as a part of his sort of canonical papers on GR. But gravitational waves are extremely weak. And consequently, even though they were predicted in 1915, they weren't first detected until almost exactly 100 years later in 2015. That detection called GW 150914, as is given by the name, it was detected on September 14th of 2015. It was detected by the two gravitational wave detectors we have in the United States. One is in Hanford, Washington, the other one's in Livingston, Louisiana. And I've showing here a plot showing what that looked like. So this is essentially a spectrogram. On the y-axis, we've got frequency. On the x-axis, we've got time. And this is what the channel looked like in Hanford, and this is what it looked like in Livingston. And you see this characteristic chirp pattern that we expect for gravitational wave from binary mergers. And this happened within 7 milliseconds of each other of these two detectors. And based on the time coincidence and morphology coincidence, we were confident this was a gravitational wave. And we later determined that this was specifically a wave from the merger of two 30 solar mass black holes that were about 500 megaparsecs away, which is about 1.5 billion light years. And for this first detection, the sort of three kind of founders of LIGO, Ray Weiss, Barry Barish, and Kip Thorne, won the Nobel Prize in Physics in 2017. Like I said, that detection, excuse me, it was detected by the two US interferometers, LIGO Hanford and LIGO Livingston. And these are two interferometers where each arm is about 4 kilometers, no, not about, is exactly 4 kilometers long. And since then, we sort of have this growing global network of gravitational wave detectors. So shortly thereafter, the Italian detector Virgo came online and has been jointly observing with LIGO ever since. In addition, there's a detector that's being built in Japan called Kagra that recently just started up and is really going to join the network in the next few years. And there's a planned detector in India called LIGO India, and we hope that should come online in the mid-2020s. There is actually also an interferometer here in Hanover called GEO, but its arms are a little too short for it to be sensitive to the sort of astrophysical signals that we detect with these things. So it's more of a sort of a staging ground for new technologies. And as these detectors they've been getting more and more sensitive, and consequently, we've been, since that first detection, have really had a large number of additional detections. This is a plot that was put out by the LIGO Scientific Collaboration after their most recent observing run. So the blue dots here all represent binary black holes that have been detected. And then we've also detected a couple of binary neutron stars, which are down here. And this is what the LSC, that's short for LIGO Scientific Collaboration, has detected. But LIGO also makes their data open to the public after some time. In fact, us here in Hanover, even though we're no longer in the LSC, we've been able to analyze this data and produce our own catalog. So this was our most recent one that we put out a little over a year ago. And this is showing all the binary black holes we detected. It was mostly consistent with LIGO, although we actually did manage to pick up a couple extra detections that the LSC hadn't found. And we're planning on creating another one of these catalogs, hopefully come out this summer when the LSC releases their latest data. So these are, like I said, these are all binary black hole detections. And what sort of things can we do with that? Well, the first thing we need to ask is, well, what sort of parameters can we measure with these gravitational waves? So if you have a binary, again, you've got these two stars going around each other. Each of the, in this case, black holes, each have their own mass, M1 and M2. So that's two things you can measure. And each of the objects can be spinning, so that adds another 6 degrees of freedom that you can detect. And then finally, there's the location and orientation of the binary with respect to the Earth. And all these parameters affect the gravitational wave that's emitted, how the frequency evolves and the amplitude evolves with time. And by studying that, we can figure out what the parameters and masses, say, of the binary were. To illustrate that, I have this animation here. So we have our two black holes orbiting at some distance away, and then we're observing them here on Earth. And that produces what we call the strain, which is this gravitational wave here. And in this case, where we have two 30 solar mass black holes, this is the sort of gravitational wave you would expect to see. And if I change the masses though, so now I'm increasing the mass ratio, you can see that the gravitational wave that you end up getting has lower amplitude, it's longer, has different phase characteristics. And so this is just representative of how observing the gravitational wave, you can learn about the parameters of the binary. That's the case for two black holes. If you're looking at two neutron stars, you pick up additional degrees of freedom, namely what we call the tidal deformability, which is basically a measure of how squishy the stars are. And as the stars get closer to each other, their mutual tidal forces cause them to deform, and that also imprints on the gravitational wave. By measuring that, we're able to learn things about the neutron stars, and I will be talking about in a few minutes, even measure the equation of state of their interior matter. So that's how things are supposed to work in theory. In practice, though, it's somewhat challenging to do this. And that's because, like I said, gravitational waves are very weak. So if I have my binary at some far distance away, it's orbiting around and emitting that gravitational wave, in theory, this is what the wave should look like that it's emitting. But by the time it gets to here on Earth, even with our very sensitive detectors, the actual signal, when you look at it in noise, actually looks something like this. And in fact, this was actually a rather significant detection. It was GW 151226, but the actual signal, as you can see, is very much buried in the noise. And so for the most part, you can't just like stare at the data and magically know what caused the gravitational wave. And so to really learn about the source of the waves and learn about them, we need to use sophisticated data analysis tools, specifically Bayesian inference. And there's a few different packages out there that do this. I'm a primary developer of one called PyCBC, which is sort of one of the de facto ones that's been used both by LIGO and those of us outside of it. And I'm primarily to work on the Bayesian inference side of things, like trying to learn what the values of the parameters of these binaries are. I'm not going to talk too much more about how exactly we do this. In my talk next week at Cooper Union, I'll delve more into what this means. But for now, I'm just going to treat this as a black box and say, we've got this tool that takes in strain data, a model for the gravitational wave, and then spits back out a estimate for its various parameters. So for instance, here I'm showing what the estimated masses of this binary would be given this observation. And so by looking at and teasing out what are the parameters of these sources, we can do a whole bunch of science. Here I just list three sort of things that I've worked on and am interested in. There's actually several other things that people do. But three things that at least are my primary interest is one, to sort of measure the equation of state of dense nuclear matter by looking at mergers of neutron stars. Another is you can test general relativity by especially looking at binary black hole mergers. Essentially, you look for deviations in the gravitational wave from what you expect from GR. And then in general, there's also just by searching and cataloging and measuring the parameters of these things, we build up libraries of their masses and stuff, and you can do general astrophysics and learn about, say, stellar formation channels and things like that. And down below here, I list a few of the recent papers that I've put out that touches on each of these things. But in the interest of time today, I'm just going to talk about the physics of dense matter, so how we can learn about the nuclear equation of state from these mergers. Yeah, let me have a glass of water. Okay, so nuclear physics with gravitational waves. So how can we do this? So first of all, if we take a step back and think about nuclear physics, I'm made of protons and neutrons. We basically all are. We're all very familiar with baryonic matter, and baryons are made up of quarks and that are held together by the strong force, and this is all sort of described by quantum chromodynamics, QCD. And QCD has been around since the 70s. It's part of the standard model. But QCD can be rather difficult to solve, and consequently, there's a large part of phase space that we really aren't sure what happens to matter. So I'm showing on the right hand side here a QCD phase diagram, or at least a sketch of what we think it looks like. And so we have on the y-axis temperature, and x-axis net baryon density. And so for instance, here would be nuclear density. And while we are very familiar of what matter does at these sort of lower densities, as you go to higher densities, especially for cold temperature, we're really not quite certain what happens, because we can't solve QCD in this regime. And we also really can't build experiments here on Earth to probe this region. Based on things like lattice QCD and particle accelerators, we have some idea of what happens at the higher temperatures. In particular, we expect that as you go to higher temperature, higher density, the sort of quarks inside the baryons kind of become deconfined. You can basically think of it as like the neutrons and protons kind of melt into this sort of quark gluon plasma. But how that happens, especially at this low temperature, and what the characteristics of the matter, the quark gluon plasma, it's kind of unknown. In particular, one of the major questions is there a first order phase transition from nuclear matter to this quark gluon plasma, or even things like sort of color superconductor. Another way to think of this is if you consider just fixing the temperature, the low temperature, you look at a pressure versus energy density diagram. Down at nuclear densities, or up to around 1 to twice nuclear density, we have a good idea of what goes on. And then at extremely high densities through perturbative means, we have an idea of what goes on. But in this in-between region, we really don't know what the equation of state of matter is. Fortunately, though, neutron stars sort of transverse this area of phase space that we don't know what happens. So if you imagine starting from the outside of a neutron star and going in towards the interior, as the pressure builds, you kind of traverse this region. And so by observing neutron stars, and such as neutron star mergers, we can begin to learn and fill in what happens in this unknown region. And we had exactly that opportunity. A few years ago, there was a detection of a binary neutron star merger called GW 170817. This was observed both by in the gravitational wave channel by the LIGO and Virgo detectors, but it was also actually observed by telescopes, because And after the merger happened, you had this huge ejecta and quite a bit of electromagnetic radiation released that was observed across the electromagnetic spectrum. And so you're able to really truly do multi-messenger astronomy with this thing. And one of the key things that you could do is start to constrain the equation of state of matter in that region that we're very unfamiliar with. And there's been a whole slew of papers that did exactly this. And I'm going to talk about this one that I worked on with a few of my collaborators. Oh, sorry. Is there a question? Okay. Okay, I'll keep going. So yes, in this paper, I worked with some nuclear physicists, particularly Ingo Tooze, who works at Los Alamos. And Ingo works on this question of what is the equation of state of matter. And so he provided me with a set of equation of states that we could compare with the data, the GW170817 data, to try and see which equation of states were most likely to be correct. And he actually provided me two sets of possible equation of states, one where he used a theory that describes nuclear interactions called chiral effective field theory up to nuclear density. And then beyond that, he used an extrapolation routine to sort of extrapolate into the unknown region. In the second set of equation of states, he used this nuclear description of matter up to twice nuclear density. It's not really certain if you can actually push this chiral effective field theory up to that. And that was actually one of the things that we were looking to investigate with this project was, is chiral effective field theory a good description of matter up to twice saturation density? So we took these equation of states. When you have these two sets, by using something called the TOV equations, you can convert these equation of states into relationships between the expected mass and radius of a neutron star. So for each one of these lines that we have in pressure versus energy density, you end up with a line relating mass and radius. So this was our set of possible equation of states where we used nuclear description of matter up to nuclear density. And this is what we got when you go up to twice nuclear density. So this was sort of our prior, and then we turned this through our Bayesian inference and used the gravitational wave and EM data. And this was the result we got. This was our posterior. So here I've colored each of the black lines. The darker the line is, the more likely the equation of state is to be correct given the data that we had. And you can see that we were able to get some measurements both on the mass and radii from this, and also constrain some of the possible equation of states. We also were able to get a estimate of what the radii of a 1.4 solar mass neutron star was. But I would say the main takeaway from this, though, is if you notice the set of equation of states where we used this nuclear description of matter up to twice nuclear density basically agreed with the data just as well as where we only used that description up to nuclear density. And because this nuclear description of matter, this chiral effective field theory, doesn't really involve quark gluon plasma, it kind of suggests that there is not quark matter between these two densities. It's not, I can't say that there definitely isn't, it's just that you can use a nuclear description of matter up to twice nuclear density and still be consistent with the data, at least the data that we had so far. Now, that was interesting, but one of the things with this, though, is we had sort of predefined equation of states that was provided to us, and we're just sort of constraining things this way. But what we really ultimately want to do is really try to dig in and see what can we learn about the nuclear physics. So a project that I'm working on right now with Dake Zhu, who's a grad student at the University of Washington, is to sort of build equation of states on the fly and sample over sort of nuclear parameters in our Bayesian analysis, and do this on the fly while we're analyzing both the gravitational wave and EM data. And one of the questions that we really want to try to answer is there a first order phase transition to quark matter, at least that we can observe? And more generically, can we hope to directly constrain some of the nuclear parameters that go into building these equation of states using the data? This is very much a work in progress, but I can show some preliminary results. first of all, as to that question of do we really constrain some of these nuclear parameters? Generally, not really, not with at least with GW 170817. We are basically finding we're getting prior in, prior out for most of them. The one thing that we do somewhat get a sort of constraint on is actually the one that we're most interested in, is this question of is there a first order phase transition? So I kind of am showing that here. So this n critical is the density at which we sort of introduce a phase transition. And then delta E is the strength of that phase transition. So delta E of 0 essentially means there's no phase transition. So we have these set of equations of state that we're trying, and we're seeing, does the data support a phase transition? And basically what the preliminary results seem to be is, if you switch from a nuclear description of matter at anything below twice nuclear density, and you kind of need to introduce a first order phase transition to be consistent with the data. However, if you use a nuclear description of matter up to twice density, then you don't need a first order phase transition. So there's this kind of degeneracy, at least, that you can't quite untangle with the current data. And I think really to try and dig into this more, we're really going to need more observations in the future. And so that brings me to the last bit in my talk, talking about what sort of things we can expect to do in the future. So within the next few years, as I was saying earlier, we're going to have more detectors coming in line, but also more sensitive detectors. So in the near term, in 2022, the next observing run of advanced LIGO will happen, and the detectors should be even more sensitive than what they are now. And in that, also the Japanese detector, Kagra, will be joining. More further afield in 2025, there'll be an upgrade to the LIGO detectors called A+, and this should have about 3 times more sensitivity than the current detectors. And around about 2030, it's hoped or planned that there'll be yet another upgrade to the detectors called LIGO Voyager, and that should have even 6 times as more sensitive as the current detectors. And things really start to get interesting in the 2030s. So in the mid 2030s, it's planned for a space-based gravitational wave detector called LISA. And this will be sensitive to much lower frequency gravitational waves, and therefore a whole different class of systems like supermassive black holes. And then in the late 2030s and 2040s, there's plans both in Europe and the United States to build what we're calling 3G detectors. So in Europe, there's this plan to build what's called Einstein telescope, which will have 10-kilometer arms. And in the United States, there's plans in the works to build Cosmic Explorer, which will have 40-kilometer long arms, so 10 times the length of the current LIGO detectors. And with these things, we'll really be able to do really great physics and learn new things at all different length scales. Oh, actually, yeah, I forgot. Here's just a demonstration of how that sensitivity will improve over time. So on the y-axis here is what is called strain noise, x-axis is frequency, and this is essentially a measure of the average amplitude of noise in each of these detectors. So the lower these curves go, the more sensitive the detector is. And when you get into like Cosmic Explorer, especially on the right here is a diagram showing what sort of systems will be sensitive to as a function of redshift. And when you get to Cosmic Explorer, will basically be sensitive to all neutron star mergers and binary black hole mergers out to redshifts of 10, which given that once you get beyond that redshift, you just run out of neutron stars and black holes because it's too early in the universe, will be sensitive to every observable binary black hole merger and potentially binary neutron star merger in the universe. And with that, you can really do lots of different science. One thing on the binary neutron star end is you can hope to start to detect the gravitational wave that's emitted after the merger. So you recall earlier, you end up forming this hypermassive neutron star, and that has some asymmetries and ends up emitting gravitational waves. And from that, you can learn things about the sort of more hot equation of state. And that's sort of represented here. So again, this is strain amplitude versus frequency, and I've plotted a few simulated signals, and this jiggly bit at the end is what you expect to get from the post-merger signal. And there's this characteristic frequency that arises from that, that you can, by measuring, you can learn about the hot equation of state. And I also think one thing I'm kind of curious about is you could also use this as a cosmological probe to sort of measure the Hubble constant out to larger redshifts. And another possibility is if you have a neutron star around a black hole, if it gets tidally disrupted, you can also learn quite a bit about the neutron star and also maybe potentially use that as a probe of, say, the Hubble parameter. That's only just one aspect, though, of some of the things that can be done. But to do these things, we really need to build some more advanced data analysis tools. And for instance, to observe that post-merger signal, you need some more sophisticated routines and things that involve what's called a transdimensional MCMC. There is already a package that does this called BaseWave, and actually a whole bunch of work has been done with BaseWave, very, very good work, and I'm showing some things here. But the sort of tools that BaseWave implements, I think, could be even more broadly applicable for other things, including some of the testing GR things that I'm interested in. But at the moment, BaseWave, I mean, it's very much tied to gravitational wave data analysis, and it's also can be a bit difficult to contribute to if you're not in LIGO. So one of the projects that I currently am working on, and I was worked on this past summer with an undergrad intern I had, Richard, was to start building sort of a Python-based sampler that can do some of these fancy transdimensional sampling routines, and what we hope eventually to be able to replicate the sort of BaseWave analysis type things, so you can do things like do science with the post-merger signal. Of course, if we were just looking to replicate BaseWave, it really wouldn't be worth it, but the main goal here is to do other things. Like, for instance, I think you could use this to test the no-hair theorem via sort of a black hole spectroscopy. And the main reason why I think this could be quite useful is being Python-based. It should make it easier, especially for students, to contribute to this research. And more broadly, this is just one aspect of something that will be sort of my overarching goal of my research over the next few years, is to sort of take these tools that we've been building for LIGO and start getting them ready to do these analyses with LISA and the next generation of detectors to sort of investigate what sort of science can be done with it, and also to make the science case, especially for the 3G detectors, since they haven't been funded yet, to really make sure these things get built. And so by building tools, especially make them Python based and building a community that's very interactive, and hosting training workshops, so I've already hosted a couple and plan to host some in the future. I hope to really enable broad participation in this sort of burgeoning field of multi-messenger astronomy, and that's going to be a key focus of my research to come. So I'm over my 25 minutes, so I'll just leave my summary slide there and say thank you and ask for any questions.
So clapping for everyone. Let's start. So Sigurd has some questions in the chat, and I see some folks will raise hands. So why don't we start with Sigurd, and then Shirley, and then Will. Sigurd.
Okay, I'll just read them up then. I think in one of the early slides you showed an overview plot of current detections, and it looked like there were more than just one binary neutron star merger on that plot. Is that right? If
yes,
so,
that's right.
How much better limits could you get if you could include the other ones in your analysis?
Yeah, so there's been one more 1904 25. I actually do have hold on, I have a plot where I involved that. The short answer is you don't get that much better, because that signal was a bit weaker, and so we weren't really able to measure the tidal parameters that well, so the constraints aren't that much different. This plot here, if you ignore the green thing, but this is the sort of constraints we got where I folded in both 1708-17 and 1904-25, and they're essentially the same, because that particular one wasn't that much stronger. So unfortunately, we haven't had any other detections, at least that I know of anyway. Like I said, I'm not in LIGO anymore, so I don't know. There's still some data that has to be released, although based on the GCNs, I don't expect there to be any others that can further constrain this. So we'll probably have to wait until the next observing run to get much better constraints, at least from the gravitational wave side.
Okay. My other question was that with these huge sensitivities of Cosmic Explorer, would you end up with confusion from many mergers going on at any given time?
Yeah, exactly. Yes. And that's actually one of the challenges to doing data analysis with those detectors. And one of the things that will be something that I'll be want to work on over the next few years is really understanding how you can separate that out. It's another reason there's been that transdimensional MCMC thing I mentioned. That's another application of that to sort of separate out sort of overlapping signals. And so, yes, that is going to be a major challenge with those.
Thank you.
Shirley?
I'm kind of curious with the community tools that you're thinking of building, what kind of people or computing resources you want to leverage if you do come to CCA?
Okay, good question. Well, first of all, on the computing resources, yes, you do need multiple parallel processors at least to do some of these analyses, although we're working on methods to sort of speed this up. So for instance, you can now analyze, do parameter estimation on a binary black hole with a laptop. You just have to set it running for a day. So you do need, like we have a rather large cluster here that I make a lot of use of. For the parameter estimation thing, you need, it's more sort of HPC computing, so high performance computing, because you have to have a lot of rapid communication back and forth between processors to make good use of this. Although one of the things that I'm trying to work on with that sampler that I was mentioning that I had Richard working on is to reduce that back and forth communication, so you can don't need such low latency stuff. As far as the tools though, so yeah, one of my interests, although because we don't really have any astronomy observers here, is to try and do more joint analyses between gravitational waves and telescopes. That package I mentioned that I work on, PyCBC, we're sort of working toward a plug-in idea with it, where if you're an astronomer and you're an expert on, I don't know, say you are an expert on kilinovae and you have you know how to analyze, say, like Rubin observatory data, and you have a likelihood function, that you could easily plug that into PyCBC to do a joint analysis without even having to really modify the code itself. And it's possible to do that with Python. And so that sort of generic plug and play kind of idea is the thing that I want to try and work toward, and potentially work with other people there at the CCA on doing.
Thank you.
Mm-hmm. Any other? I think I see, Will, you have a hand up?
Yeah, I'll jump in. So I'm curious, I kind of have a follow on, I guess, to Sigurd's first question in terms of binary neutron star mergers. If you could just dial up your favorite events, what do you want next? Do you want, massive compact neutron stars with high signal to noise? Would you rather have kind of a weak signal with a lightweight puffy neutron star? What's going to get you the best constraints and get you to these constraints on phase transitions fastest?
Yeah, I would say the more massive, the better, and because then you can see if there's, like with a phase transition, if you have one, then you end up essentially with a kink in these diagrams. So if you can really measure something at high mass and it's very compact, then essentially the only way that you could connect that would be by a kink in the equation of state. That would be sort of a smoking gun. And actually, to that end, so just to be totally honest, so there's this NICER, is this X-ray observatory on the International Space Station. They're observing pulsars. In fact, I think hopefully they should be releasing their latest results sometimes in the next few months. That's actually probably going to provide some of the better constraints over the next few years. And so folding that data in, I think, will really help to constrain this, because really ultimately what you want to do is you want different spots in this mass radius diagram so you can map it out and see, are there any discontinuities that you have to connect? Yeah.
Quick follow on. Have you tried what is truly insane, but could be interesting, to pretend that the lighter object in 1908-14, which is the really extreme mass ratio, the 10-to-1 mass ratio in spiral, you know, the lighter object's about 2.6 solar masses or so. If you pretend that's a neutron star, you basically rule out all the equations of state, right? So what does that get you?
You do.
It's insane, right? But it's an interesting question.
Yeah, that's a good question. I haven't actually looked at treating the smaller object in 1908-14 as a neutron star. Actually, the work I did on that one was actually just assuming it was a black hole and doing a tested GR with that. As you can see, I mean, in this diagram, that would actually automatically rule out all the equation of states that we had here. So you'd really have to go back and generate new things. Yeah, I don't know. I haven't really looked at that. It would be an interesting thing to do, although that actually touches on another, I think, challenge going forward, especially with some of these more high mass things. There's this ambiguity when you get above 2 solar masses of, is that a black hole or is it a neutron star? And if it ends up, especially if it's very compact and you can't really measure the tidal deformability at much, you know, it's kind of, personally, my thought though on that is better to play it conservative, because if you assume it's a neutron star, it's kind of, you know, it's very extreme and you end up ruling out a bunch of things when you may not be very confident that it is. And I mean, frankly, you know, there was this talk of a mass gap between 2 and 3 solar masses for black holes, but that wasn't, there's really no theory behind that. It was mostly just an observational thing. So my personal thought is 2.6, it's a black hole. So yeah.
Cool, thank you.
Glennis?
Yep.
I apologize because your audio went out for a while for me, so I may have missed something.
That's
but
right. That's right.
In my understanding of the subject, as you were saying, the strong constraints that are so far on neutron star mass radius relation, and that NICER will be really powerful for that. But I didn't hear you speaking much about the deformability, which in fact, in the example of 1708-17, is problematic for some models. And so are you not including that in your own modeling, or did I just miss that part?
Oh, yeah, no, sorry. I was only just showing mass radius here, but the thing that we're actually measuring with the gravitational wave data is the tidal deformability. It's just that we're assuming an equation of state, and that immediately links together both the mass radius and the tidal deformability. I just show mass radius here because it's easier to explain to people. But yeah, and actually the thing that we're actually constraining is the tidal deformability. Yeah.
Okay. And then related question about your equation of state. When you described it, you called it a chiral perturbation theory, I think you said. And
I meant to say chiral effective field theory, sorry.
Oh, sorry, that's what you said. And that's what I meant to say too. But they break down into 2 categories, the ones that are typically in use. One is without hyperons, things like lambda and sigma particles with a strange quark in them, and ones that don't include them. And we know the hyperons exist, so the correct ones should be the ones with hyperons. And those totally fail. They have they don't allow you to get to high mass. They wouldn't miss yours because your masses in this particular case are okay. But were you studying viable equations of state? Are you sure?
I think so. Yeah, the ones that we're using here didn't include hyperons.
Did not. Well, that's exactly the problem, because we know there are hyperons in nature. So to simply leave them out because they predict a wrong answer That's in fact, I believe, one of the strongest arguments for needing a phase transition. It's an indirect argument that if we put all the physics in that we know to be there, we get a wrong answer.
Yeah, fair enough. Fair enough. Yeah, I mean, I'm kind of relying more. I mean, I'm not a nuclear physicist. I'm relying on the nuclear physicists to tell me what's adequate. So this is what my my collaborators have provided. So yeah, but yeah, that's a good question.
Do we have other questions? As you look over the next few years for analysis, what do you see as the the biggest conceptual challenge for doing the modeling? You mentioned a few.
Over the next few years?
Yeah.
Yeah. So one of the big ones, at least talking about black holes anyway, is, and we've already had this with, there was this event 1905-21. Let me bring, well, I'll show this anyway. Yeah, there was this event 1905-21, that was the merger. Well, the initial estimate from the LSE was it was the merger of basically an 80 solar mass, roughly an 80 and 90 solar mass black holes. But the thing was, the signal was extremely short, and so you're really observing the signals that we're using really have to come from numerical relativity at that point. But like, for instance, when my colleague Alex and I reanalyzed this thing using different waveform models, we actually found that the most likely scenario was it was 180 solar mass, well, actually I should say 17 solar mass black hole orbiting into 180 solar mass. That's quite a bit different, it has very much different astrophysical implications. And the big problem there is because that would be large mass ratio, and we also found it was highly spinning, we don't have very good models, waveform models at that point, because NR is very hard to do. And given that we've already observed one of these, chances are good we're going to observe more of these in the next observing run. And so not having good models at high mass ratio, high spin is going to be a real challenge to both doing astrophysics and if you want to do any sort of testing GR with these signals, which is a shame because these are kind of the most interesting signals that you could look at because they're very dynamical. On the neutron star side of things, truthfully, I don't think the models, I mean, for the amount of signal to noise ratio that we have and we'll probably expect to have in the next few years, I don't think there's going to be any big modeling issues, at least from the gravitational wave side of things. People have made enough advancements there. I think the bigger question there is more if you want to do the more nuclear physics type things, sorting out any sort of unexpected degeneracies or things like that, like I was talking about at that earlier. So, and actually, okay, now that I say that, yeah, so the other thing, maybe more with neutron stars, and I was mentioning that earlier with Will's question, is this question of if you get into objects that you determine the smaller or one of the objects is anywhere from 2-ish to 3 solar masses, is that a neutron star or is that a black hole? And figuring out what to do with that, that's going to be a challenge. I mean, the conservative thing to do is if you want to constrain equation of states, don't include such objects, but then conversely, those could be the most interesting objects to use. So,
how high a signal to noise do you need to really, future 2.6 solar mass system to be able to separate out the neutron star from black hole based on the gravitational wave signal?
That's a good question. We've been looking at that here. It depends a lot on what the actual equation of state of these things are. So 170817 indicated that the they're actually quite compact, and the tidal deformability is small.
Right.
The smaller that value is, the harder it is to distinguish between a neutron star and a black hole. So for instance, we have a student here that's been looking at this for the next few generations of detectors. If you take, so if you look at our posterior here, if you take sort of the more stiffer end, so the sort of more bloaty equation of states up here, then you can actually distinguish quite well the difference between a neutron star and a black hole if you had a system at the same distance of 170817 and even at like twice distance. But if it's at the more compact end, even with A+, it's looking like you're not really going to be able to distinguish a neutron star from a black hole in that case. And so that's, a challenge, but is also an argument to build the next generation of detectors. So.
Good. Gladys, do you have another question, or you just kept your hand up? Sorry. Gladys?
Apologies, I just didn't take my hand down, but I was typing a question to him, but with the apology that he may have covered it when I was having my audio difficulties and trying to reconstruct. Did you in the end talk about the no-hair theorem test? It seems strange you would have skipped it, but I just didn't hear that part. Maybe you talked
no,
about it,
I didn't, because I didn't. No,
Can
I
you
didn't
tell us
talk
in
about it
1 minute?
because for time. Yeah, sure. So yeah, no hair theorem tests. So the sort of canonical approach that people take or to do this, sorry, let me take a step back. First of all, just so everybody's on the same page, the no hair theorem basically says that any black hole, at least astrophysical black hole, is entirely characterized by its mass and its spin, and regardless of what fell into it beforehand. And this is like a key underpinning of GR. And so one thing that you can do is if you have a perturbed black hole like you do after two black holes merge, that perturbation that you get ends up getting radiated away. And the gravitational wave that's emitted during that time is a sum of quasi-normal modes, which means a sum of damped sinusoids. A consequence of the no-hair theorem is that even though you have this infinite sum, this infinite spectrum of quasi-normal modes, the frequency and damping time of all those modes should be described by just two parameters, the mass and the spin of the black hole. So a test of the no-hair theorem that you can do is if you can independently measure those different modes from the gravitational wave, you independently measure the mass and spin from each of those, you compare it. If the black hole is a classical GR black hole and it doesn't violate GR, then you should get the same value for the mass and the spin for everyone. If it doesn't, though, if you were to get different masses and spins from the different modes, then that indicates a violation of the no-hair theorem, which is to say that the object's not a classical black hole. So a lot of people, myself, Will's done work on this, have looked at doing just those sort of tests. There are a lot of challenges to it, particularly data analysis challenges to it, because you're working with signals. I should really be showing a gravitational wave here. Maybe I can, yeah, here we go. Yeah, you're dealing with signals like the part of the signal that you're dealing with is just this damped sinusoid at the very end. So the SNR is very weak. And so you need very loud signals to be able to do things with this. But one thing, so this recent paper that I did with my colleague on these two events, 1908-14 and 1904-12, was we sort of took that idea of looking at different modes. Instead of just looking at the post-merger signal, we extended it back to the entire gravitational wave, because you actually get these subdominant modes throughout the entire wave. Let me show you, I have a plot of this. Yeah, so basically the entire gravitational wave can also be thought up of a sum over spherical harmonics. And again, as a consequence of the no-hair theorem, although kind of more applied to the initial black holes, you expect all of those modes to be described by the same parameters. Although if you're looking at the full binary, it's really 8 parameters that you have, the 2 masses and the 6 spins. But you end up getting more SNR because you're looking at the full thing. And we actually did that with these 2 recent events. And we were able to get some pretty good constraints on it. So essentially, we independently measured the mass of the, well, what's actually called the chirp mass of the event using the dominant mode and the next subdominant mode. We independently measured it, and then we compared them, and we basically got agreement with GR down to the 1% level. It's kind of shown here in this plot. And another way to look at this is if you plot M1 versus M2, so the estimate of the 2 masses, the black line here is showing the estimate from just the dominant mode, and the orange line here is showing what you measure when you just look at the next subdominant mode, and you can see they agreed extremely well with each other. So this was kind of a test of GR in that sense. The only thing though is it's a little bit trickier to connect this back to theory when you start getting into the in-spiral regime and doing this. There are maybe possible constraints. I've talked to some theorists that you can maybe use this to constrain, say, like Chern-Simons gravity, but it's a bit different because you're looking at more long-range hair there. Probably the more exciting things will be doing just the post-merger, the quasi-normal mode measurements. And again, though, that's something more probably that we'll be able to do in the future.
Yeah, I was kind of curious if there was a, let's say, some sort of a way to decide how close, how well you could probe real theories that would be not canonical GR, whether whether this sensitivity is remotely useful or not. Do you have any idea about that?
That's a really good question. I've actually, I've actually been thinking about that too. There does seem to be a bit of a disconnect at the moment between the analysis community and the theory community when it comes to testing GR. Like, people are doing all these tests, but it's not really clear if they're very actually useful at all for theory. The quasi-normal mode stuff, I think, is more straightforward, and people have been thinking about it longer. But like tests like this, and there's other sorts of tests that the LSC has done. Short answer is I don't know how useful this is to the theory community. Part of it is we don't really have a good viable alternative to GR or anything that anybody really expects. And especially to get a gravitational wave out of these alternative theories, it's difficult to do, and not, people really haven't been doing it because, I mean, even if you were to generate a gravitational wave for some particular alternative theory A and you rule that theory out, well, it's like, well, I didn't really expect that to be true anyway. So, most of these things are just doing null tests. Yeah, one thing I actually,
axions, which have been really, superradiance and axions has been very popular lately. So that would be an obvious candidate where somebody might have tried to ask, is it? But anyway, I don't want to keep everybody. I just,
so
you might have.
We should probably wrap things up. At this point, we're getting on to an hour. So let's thank Collin for a really interesting talk, and I'll see you all soon.
Thank you.
Thanks, Collin.